Today I'm gonna be discussing a demonstration on repeated measures one-way analysis of variance. But before we get to that, let me first talk about what repeated measures one-way ANOVA is and what are the conditions for which it is used. So it's similar to the other kind of one-way ANOVA, the between subjects, in the sense that it is used when you have one independent variable that is categorical, typically when there are more than two levels in that categorical independent variable, and when you have one dependent variable that is typically measured as a continuous variable. Um, However, unlike um, between subjects ANOVA that is used when the categories are represented by separate and independent samples, repeated measures ANOVA is used when the levels of your IV is collected from either a single sample that is repeatedly measured, hence repeated measures, one-way ANOVA, or separate samples that have been matched in some way in the attempt to control for an external variable. So in many ways, repeated measures ANOVA is quite similar to paired samples t-test, if you remember that particular analysis. Anyway, so for today, let's focus on this problem. So this is the background of uh, what we're gonna demonstrate today. So a certain group of researchers examined stereotypes we hold about attractive people. Subjects looked at four types of photographs of persons all unknown to them. One of a physically attractive person, one average, one unattractive, and one highly attractive. So, and then the subjects rated each photograph uh, in terms of how socially desirable that person is, how perhaps the extent to which they want to socially engage with that person, to become friends with that person. Higher scores reflect greater social desirability. So in this case, the independent variable is the level of attractiveness, um, and there are four levels to attractiveness, beginning with unattractive, um, average attractiveness, attractive, and highly attractive. Um, so there are four. So what happens is that we have a sample, and each member of the sample is shown four photographs. Um, and that the variation in those photographs is the variation of our independent variable, and there are four categories or four levels of attractiveness, and then each member of the sample are asked to rate the social desirability of each person in the photograph. Um, so we will use repeated measures ANOVA, as the term suggests, because repeatedly the participants or the sample were asked about the social desirability of the photograph that they are looking. They rated four times, one for each photograph, and hence the repeated measures aspect of that particular situation. So we want to know, is the rating in social desirability um, um, co-varying with the level of attractiveness? Will we see a pattern wherein those who are more attractive are perceived to be more socially desirable, and those who are less attractive would be perceived as less socially desirable. So we want to test if there is such covariation or such pattern that is happening in our data. And maybe we can pose our hypothesis, which states that um, one, there will be significant differences in the social desirability across different levels of attractiveness, and we also probably would would want to predict that um, those who are attractive and highly attractive are perceived as more socially desirable compared to those who are unattractive or even those who are average looking. And with that, this is our data set. So this is how you prepare your data for repeated measures, one-way analysis of variance. Um, Again, I'm using JASP as the software for the analysis. Unlike how you enter your data for between subjects, one-way ANOVA, um, the column headers here are not necessarily our variables, but rather the levels of our independent variable. And each row represent one participant. So there are 16 participants. For example, participant 1 was shown the unattractive photograph. The rating for social desirability is 35 for the average attractive photograph, 40 attractive, 65, and highly attractive, a rating of 68. So all of these scores are ratings coming from one individual, and all of the 16 participants rated the photographs, each of the photographs, and hence every case has 4 ratings, and thus repeated measures. So measured once in terms of social desirability, repeat the measurement again after showing the average attractive photograph, measured again, and then measured finally after being shown the highly attractive uh, person in the photograph. And we want to see if the variation in these levels of attractiveness coincide with the average ratings that they um, that they um, that they gave for the photographs. Okay. Um, so to run this, let's click on ANOVA and then repeated measures ANOVA. Okay. The first thing that we have to do is to label our factor. So in the context of ANOVA, again, the factor refers to the independent variable. So our independent variable is attractiveness. And we want to label the levels. So let's just copy. Unattractive, average, attractive, and one more, highly attractive. And as you are encoding these, they also appear here. Okay, so what we want to do now is to simply transfer these variables over to these spaces. Okay, let's do that. All right. So this is our initial result. Um, One thing that you might notice is that we have two tables here. One is the within subjects effect, which is essentially our repeated measures ANOVA. And then we also have here the between subjects effect, which doesn't have a result. And that is because we did not enter a between subjects factor, because we are not doing a mixed plot design or a mixed plot analysis of variance. What we're doing is a simple repeated measures ANOVA. And that means to say that this particular platform can also run mixed plot two-way analysis of variance, which we are not doing right now. So basically, for repeated measures ANOVA, we ignore this part. Okay. All right. Um, So when we take a look at the p-value here, the p-value suggests significant differences. So the variation in the means, in the average social desirability ratings across the different levels of attractiveness, is there is a significant difference being detected. However, we will also notice that there is uh, uh, we've been flagged, and it says here that the Monchi's test of sphericity indicates that the assumption for sphericity is violated. So what does that mean? When we run analysis of variance, there are certain assumptions that must be satisfied, one of which is the test of sphericity. If you remember um, the lessons we had in t-test, an important assumption is that there should be equality of variance, and sphericity is basically the same thing. What does that mean? Let us go back to our data. So if you notice, per um, there is variation per in the ratings for social desirability, um, and what we want for our assumptions is that the variation you see here is the same as the variation that you see here, here, and here. However, when we are being flagged because it seems that um, the variations among these scores doesn't seem to be equal. Either one of these set of ratings is less varied than the others, or some are more varied than the others, and that's why we failed that particular assumption. So let's double check. So let's go to assumptions check and click on sphericity test, and what we want is a non-significant p-value. If the p-value is not significant, that means to say that there are no significant differences in the variances across the different conditions, but we have a p-value that is significant, less than 0.001. So that means to say that there are differences or systematic differences in the variances, and thus we are being flagged here. Now it's not really much of a problem because luckily JASP also provides corrections for the lack of equality of variance. So all we have to do is to click on sphericity corrections, and you will notice that there will be other outputs that are shown here. So basically this is the output when there is no correction when we apply the greenhouse Geyser correction, and when we apply the Felt correction. Um, um, so for this, let's use the greenhouse Geyser correction. So we want to make our table simple, so we can uncheck none. Wait, before we do that, I just want to show you that even if we did the corrections, we practically have the same result. Um, so perhaps the assumptions would matter more if our p-value is um, near our cutoffs, but since our p-value is really way beyond or way below our level of significance, the corrections did not matter anymore. Nevertheless, just to be on the safe side, so let us uncheck none and the Hunefeld, and what we have, or the result that we have, is the one which imposes the greenhouse Geyser correction. So we are more confident with our results after implementing such correction. Again, this is not always done. This is only done when you have failed your assumptions checked, and thus we impose the sphericity corrections. Otherwise, if the variation or the variances across or in the dependent variable across the different levels of the IV, if they have equal variance, then we would not need this sphericity correction. Okay, we are just doing this because, like what I said, we failed our assumptions check. Okay, all right. So next, another thing that we want to do is, let's see the effect size. So let's go to additional options. Let's click on estimates of effect size. We will use what is the default, which is eta squared, and our eta squared output is 0.682. So this means to say, or what you can say about this is that 68.2%, so we convert this into percentage, 68.2% of the variation in social desirability ratings can be explained by the variation in the level of attractiveness. Okay. What else? What we also want is to see the descriptive statistics. We know that there are significant differences, but we don't know exactly what is the nature of this difference, and our descriptive statistics will tell us that. So this is our descriptive statistics. So these are the average social desirability ratings and their corresponding standard deviation values. So we will notice, at least numerically, that what we suspected was correct. Those who were less attractive have lower social desirability ratings, and those who are more attractive have higher social desirability ratings. What we don't know yet, however, is where exactly are the significant differences. It seems that it's kind of obvious that there's a difference between 44.8 188 and 67.188, but what about 44.18 and 45.25? Is there a difference between those two, or between 63.5 and 67.18? Is there a difference between those two? And so to determine where the actual differences lie, we have to run our post hoc test. So let's click on post hoc, and Let's transfer our independent variable to the other side. Okay, let's use what is in the default, which is home, and in our output we have here our post hoc output. So given that we have 4 levels, we want to compare them from each other, and thus we have 6 comparisons. So we compare attractive and average, attractive and highly attractive, attractive and unattractive. We compare their means, and so forth and so on. And this is the result. So again, if the p-value is less than our alpha level of 0.05, so that means to say that there is a significant difference between them. Now before we take a look at where the differences lie, let's also try to visualize this. So let's go on to descriptive plots, and click on attractiveness and put it in the horizontal axis. Okay, so this is our descriptive plots. Let's also click on display error bars so that it will show our confidence interval. Let us expand this a bit. Okay. All right. So the comparison between unattractive and average, let's look for that. Average and unattractive, is there a significant difference between these two means? No, there is none. The p-value is not less than 0.5. Between unattractive and average, where is that? Unattractive and average, is there a significant difference between these two? Unattractive and highly attractive, rather. Unattractive and highly attractive, is there a significant difference? Yes, there is. So looking at the p-values, it seems that there are differences in the means, except for the mean social desirability for unattractive and average looking. What is kind of interesting, however, is this. The social desirability of those who are attractive and highly attractive, where is that? And highly attractive, so this one and this one, the p-value is still significant. However, visually it doesn't look as good. If you notice, there is a lot of overlap in the confidence interval, and so that means to say that there is a possibility that the actual population means are the same, and within those the overlap of the confidence intervals. So that's something that I would be cautious about when interpreting. I'm kind of confident about this comparison and this comparison and the comparison between unattractive and highly attractive. I'm somewhat a bit worried about the comparison between attractive and highly attractive. If there truly is a difference that is meaningful, the p-value suggests that there is. However, we do not simply rely on our p-values. It's also a good practice to look at the confidence intervals and the visual representation. So this is something that I'm a bit skeptical about. Okay, and maybe that is something that you need to explain or mention also when you write the report. All right, so that's it. That is how you run repeated measures one-way analysis of variance. I hope you learned something, and see you in the next tutorial.